Whether my screen is visible?
Yes, sir.
So as I promised last week that we will do some problems on backpropagation algorithm. So today's class is going to be beautiful in the sense that we have to really understand the working of this BPA. And as I told you that basically you'll be surprised that your baby is learning. And whatever the derivation we have done, that may looks bit dry to you. And but all those idea and somebody asked means how this internal changes are happening. So I told because this is what the formula finally we derived and it's indirectly affects all those things. But when we do use paper and pencil method and actually you trace the algo, you'll come to know that in reality how it really actually works. So we'll see it today. But before that, I want to just tell you very simple thing. So mostly I'll do today board work. So let's say this. And as you know that this basically this BPA works in two phases, two paths, I should say. What is called you have this forward pass and backward pass. Okay, backward pass. So let me take a very simple one single neuron. You may say, yeah, what is there in this single? Just wait a minute. I'm going to use one concept here. Let me say this is fixed at say x0, which is +1 to account for the bias, x1, etc. And then let's say xm. And here you call as a wj0. This is wj1. Likewise, this you call as wjm. So finally, this is say yj output. Let's see. Now, once you have this system, so we know that basically it is something inside and actually it works like this. As far as signal flow graph is concerned. So we have this x0, x1, let's say xm. And here I have this, say, this is my yj. So we know that in this case, yj is nothing but pi of, I'll write wj0 x0 plus wj1 x1 plus wjm xm, which we simply call it basically summation, and I equal to 0 to say m and wji xi, right, which we call finally some vj. Okay, so this whatever you are computing here, straightforward, this is nothing but our forward signal. Forward signal. When I say forward signal, as I told you last class, during the forward pass, we straight away compute the value without any change in the synaptic weight. Synaptic weight change comes into effect during the backward pass only. So it's a straightforward. So whatever the initial values of the weights you have, using that you start this. Okay. Now, so this is simple to say that how a forward signal works. Now I'm going to abstract it and basically, uh, but before that, let me summarize whatever the algo we derived last class. So WJI and whatever you can see, change in synaptic weight for the neuron J, which is triggered by the input I, is nothing but eta times delta J n and y n, where delta is a local gradient corresponding to the jth neuron and y is the input from the previous layer. Okay, where we saw that delta Jn can be written as Ej phi prime Vj n if J is an output neuron, or you can say that neuron in the output layer, or if it is not so, so this is phi j bjn k delta k n wkjn, right? And this is j is a hidden neuron or neuron from the hidden layer. So this formulas we had. Now here, this phi, that is the activation function, is generic in nature, which we can be anything. So we have considered two cases. In one case, we have considered that phi vj as a sigmoid function, 1 plus exp minus avjn, let's say whatever, okay? And with that particular application, we saw that our delta value changes with those when we apply all those things. Changes in the sense that we are writing formula in more simplified form. Overall formula remains same. That is A djn minus ojn oj 1 minus ojn. I'll explain once again what is happening. And then we have A yjn 1 minus yjn k delta kn wkjn, right? So this is j output neuron. If it is output neuron, j is a hidden neuron. So this we have seen all those things, where O is nothing but the output of the neuron in the output layer. We are denoting by O. That's all. I could have denoted by Y also, but it's to indicate that anyway this is output neuron. So let me say it's a O. And Yj is basically the output of the jth neuron. And here we have not written O because the jth neuron, this belongs to some hidden layer. Okay, that hidden layer could be anything, first, second, or third, depending on the depth of your network. Now this we can simplify further. Let's say that the slope parameter A is equal to 1. Simply, let's say A equal to 1 if I want. So if I can write it, let's say, let A equal to 1. So you know that this will be not there. So directly I can use that. Now, so we take one particular network, and I'll take a little complicated network. It's almost a 3-layer system. So let me say one. Don't worry about the intuition logic behind this. My objective is to trace the BPA. Let me call some here. Let me call this as A, B. Just name for this neuron so that we can refer. Alpha, beta, gamma. Capital A, capital B. I could have written 1, 2, 3, 4, 5, 6, but that may be confusing sometime. And this, what should be the name of this weight? Can anyone of you tell me? What should be the name of this weight? Please speak out, bhai. Anyone? What should I write here as a weight name or the variable? Hello? Are you there? Okay.
W11.
Not W11. WA1. Remember this? We said this earlier. When I say WJI, I indicates input from previous layer. Input from previous layer. And J is the neuron ID, you can see. Simple. So this input is coming to the neuron A. So this is WA1. Likewise, of course, it's a fully connected network. So one will be going to here also. Now we can say it is WB1. B of neuron getting input from the X1 from the previous layer. Likewise, I can say this as WA2. Similarly, I can say this as a WB2. Okay. Now, this I can. What should I name it now? Anybody? What should I name it?
W alpha A.
Yes, W alpha A. Likewise, we'll write it as a W beta A. This is a W gamma A. Similarly, I can say this way. W alpha B. W beta B. And similarly, W gamma B. Same way we'll write for these things. So it is W A alpha. And this will be W B alpha. This will be W A beta. This will be W B beta. Okay, and this will be W A gamma, and this will be W B gamma. Okay, let me call as a OA, output of output neuron A and output of output neuron B. Okay, so our objective is that to show one pass completely, forward and backward pass, and that idea later will generalize to deeper network and a more deeper network. So let's say this is a very nice toy type example, and this we are doing it for sake of understanding. Okay, now for this, first we have to apply forward pass. So forward pass will be done using the same approach. So you know, and that's why I started with this process. So you know that when something is come to like this, how do you calculate yj? Yj is something like this. Now with this particular process, let's say it has been followed, and I have effectively 7 neurons. So I have, let's say, calculated already YA, YB, Y alpha, Y beta, Y gamma, OA, OB. To say that this forward pass, forward signal you have calculated, the process which you explained earlier. Now the question is, now this has been done, I have to back propagate. In this, D is that when you apply at nth time instant input, corresponding to that input, what was the desired output? That is the D. Now, we'll start with OA. Okay. We'll start from the output layer. When you start from the output layer, so first of all, when we back propagate, you have to first find the local gradient of that particular neuron. Means, first, if I have to start, so I have to go for delta A. I'm not writing N anymore, just for sake of simplicity. So as for this formula, so I'll just write it once again here. Here I'll write in short, delta J N is nothing but dj minus oj, oj, dj minus oj. If it is j is the output neuron and it is what is that a. So it is yj 1 minus yj k delta k wkj if j is a hidden neuron. Okay, now this thing will be there with us. Now with that we'll write here. So dj, I'm talking about the neuron A. J is identity. So what is the identity of that particular neuron? A. So I'll write dA minus OJ. OJ means OA, this particular output only. OA. Then OJ, OA. And here again, sorry, here it won't be DJ. It is just 1. Okay. So 1 minus OJ. So 1 minus OA. Likewise, we'll calculate dB. That is the local gradient for the second neuron in the output layer. So as per this particular formula, it will become dB minus OB. That is the error component effectively. This is nothing but this particular error. If you remember, this is the error. That's all. So we have now OB 1 minus OB. Okay. Now once I have found this, now the question is, once the error etc. is found here, how do I propagate back so that changes happens here? Now, before I go further, I want to use one convention. Instead of writing this, let's say wji n plus 1 equal to wn plus, ji and delta wgin to say that change is happening at n plus 1. I'll be just using this notation ji plus. So ji plus delta wgin. Just a plus here instead of writing this n etc. Okay, just for avoiding this confusion because I'm just writing in generic sense. Now, when the local gradient is available, delta A, delta B, how do I propagate this error? So this changes in synaptic weights happen because during forward pass, no change happened. Whatever the initial value weights were there, you have calculated YE, YB, etc. Now, once the error is available, how do I propagate back so this change in synaptic weight happens? For that to happen, because change in synaptic weights, you know, delta wgi equal to eta delta ji. This particular formula will be remembered. So we'll just remember this particular formula. So I'll just write it here. Delta wjin equal to eta times delta jn yin. So delta A, delta B we have calculated. Right. Now we'll see this what does change happens. So change means here J I. So here I is having 3 means the input from the previous layer alpha, beta, gamma. So we'll say that first of all delta W A alpha equal to eta times delta A means the local gradient of that particular thing into input from the previous layer. So input from the previous layer WA alpha, what the input it's getting? Y alpha. So Y alpha. So likewise, so I can say that now WA alpha updated version or change is nothing but WA alpha plus delta WA alpha, which is nothing but WA alpha plus eta delta A Y alpha. In the same way, I can write other weights what A is getting. So other weights A is getting is nothing but WA beta plus I can say W A beta plus delta W A beta, which is nothing but W A beta plus eta times, and we are still talking about the neuron A only, so local gradient remains same. Only thing is, but it is getting input from the B beta from the previous layer, so it is Y beta. Likewise, I can write here straight away W plus A gamma equal to W A gamma plus eta delta A Y gamma. Is it okay? Does anybody have any doubts? So I have told you that if I have got the local gradient available here using this and biopropagation algorithm, we are able to change the synaptic weights for this particular layer, and the updated synaptic weights are this weights. These are the plus weights. Okay. Now the problem is another. This is the output layer. It was easy for us to do this. Now let's talk about this one. So before, when we apply the backpropagation algorithm, when you go to a particular neuron in the backward pass, first you have to compute the local gradient for that particular neuron. So we have to find delta alpha, delta beta, delta gamma. So how do I do this? Now this delta alpha, first of all, I should understand this. Alpha is a neuron which belongs to a hidden layer. It means I need to use this equation, not this. This equation we have to use it. So let me write first, just for avoiding confusion. Let me write once again. Delta j is nothing but yj 1 minus yj summation k delta k wk j. Okay. Now with this formula using, I am going to talk about delta alpha, which is nothing but output of this one. It is known to you, alpha 1 minus yj means y alpha summation k here. So here k is nothing but it is the number of neurons in the higher layer, and those are two, A and B. That is, when you are considering this, the number of neurons in the higher layer is this one only. That is, A and B are the two neurons. Then here we have delta k, wk, and j is nothing but alpha, means whatever you consider. So when I expand it further, I can write y of alpha 1 minus y of alpha, and when I open this summation, k once will take index A, another time it will take B. So it becomes delta A WA alpha plus delta B WB alpha. And remember that these weights are the updated weights, because now we are calculating this, so this will be writing in terms of weights of this one, but these weights are already updated because of this backpropagation. So effectively these are nothing but updated weights, you can say. Okay. Now similarly, I can find this delta beta very easily. I can say y beta 1 minus y beta, and same thing this will remain. So A and B delta k wk alpha, I can write very easily A beta 1 minus y beta, and here you say that this will remain same, w a beta plus delta b and w plus this is b beta. Remember that delta A, delta B, which we have already calculated on the output layer. Here we have already done it, right? This we have already done it. So those values are there with us. This we have already updated weights we have calculated. These are there also with us. Likewise, I can calculate delta gamma, I'm writing straight away. So y gamma 1 minus y gamma, and here delta A W plus A gamma plus delta B W plus B gamma. So this we have done. Now at this, you found this global gradient, you change the synaptic weight, you found this local gradient. Now the job is to change this synaptic weights. How do I backpropagate it? So, and also if any point of time you have any confusion, please don't allow me to proceed. Okay? Otherwise, this will be very difficult, and you have substantial portion from this chapter because this is the fundamental building block of any learning in any neural network. So this is what is happening. So we know this, we know the rule. Again emphasizing, because delta Wji and whatever is eta times delta Jn times Yin. Okay, so because we know this, it happens true. So we'll write delta Wj, J means alpha, the neuron under consideration getting input from the previous layer, which name is A, equal to eta times delta J, J means alpha, into input from the previous layer. Previous layer is nothing but Ya. See here, the input from this previous layer, alpha layer, etc. is Ya and Yb. So you have something like this. Now once you have this, so I can say W plus alpha A equal to W alpha A plus, same way, eta delta alpha Ya. So delta alpha you have already calculated here. Ya you have started calculated using forward pass only. Likewise, I can calculate straight away all those things. So I can say W plus alpha B. So W alpha B plus eta times delta alpha Yb. Done. So this two weights you got. You got this weight and this weight. Now let's talk about this and this also. So likewise, once you have done this, so we need to find W plus for neuron beta. Beta is getting input from A, which is nothing but W beta A plus delta, sorry, eta times delta, you are talking about neuron beta. So you say delta beta, and it is getting input from A. So Ya, that's all. Another one, I can say beta from B as an input. So W beta B plus eta delta beta Y of B. So you got these two values, beta A plus and beta B plus. So this beta A plus beta B plus. So these two weights you found. This you already found, this you already found, now left is 2. So straight away we can write this also. W plus gamma A equal to W gamma A plus eta delta gamma. Gamma is changing because we are talking about neuron now, and it is getting input from the previous layer, so Ya. Likewise, I could have written this gamma B, so W gamma B plus eta delta gamma Yb. Okay. So all those six weights, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 weights we have calculated. We got this all weights. We have found that. And remember this one thing. Don't you think I'm missing something? So this is updation only. So I'm not missing anything. But remember that when you calculate now, you are at this layer. Again, you have to calculate delta value for this. So when you calculate the delta value and that belongs to neuron hidden layer again, we have to go for delta A, which is nothing but YA 1 minus YA K and alpha beta gamma delta K and here WK and A in this case. Alpha beta gamma because you are at this particular layer. The higher layer corresponding to this is this, which is having three neuron alpha, beta and gamma. So we have to consider those things. So considering those things, we can write like this. Delta A equal to YA 1 minus YA and this one. K once it will take the value of alpha. So alpha W alpha A. Remember those values we have already updated. So this will take plus delta beta W beta A plus delta gamma W plus gamma A. So this we found. Likewise, we'll be able to find for delta B as well. So delta B is also straightforward. So here we'll say YB 1 minus YB and this will remain same because for next layer same alpha, beta and gamma are there. So we have delta K, WKA. I can write now YB 1 minus YB. Now here we have to write those things. That is Y alpha here, so not Y alpha, sorry. Delta alpha W plus alpha and getting from BR. Delta beta W plus beta B plus delta gamma W plus gamma B. We got the value of delta A, delta B. Now what is left to me? Still I get to the back to the input layer. So I have to change this synaptic weight as well. Okay. So synaptic weights as well when we come to this. So this is very crucial phase also. We have to just be careful again. So I can write it my delta WKJ. Again I'm just JI, which is nothing but eta times delta JYI. Again I'm reminding it. So I can write now delta WA1 means A considering taking input from the first input is nothing but eta times delta J. Delta J means delta A. YI means X1, that is the input, right? Now keeping this thing into account, I can write WA1 plus equal to WA1, whatever the value at any time instance, plus eta times delta A X1. Likewise, I can write WA2 plus means taking input from the other one, WA2 plus eta times delta A X2 straight away. And for the other neuron, that is B, we'll write B1 plus WB1 plus eta times delta B X1 and plus B2 equal to WB2 plus delta B X2. This completes this entire. Now, sometime in some books, they mention this they will mention something like W1 A1 or W1 and B1, indicating that these are the weights corresponding to layer 1, layer 2 likewise. Okay, so don't worry about this for the timing, we'll consider. Now tell me, so we have traced entire thing right from forward pass to backward pass. Does any one of you, so effectively all these are the learning parameters, all synaptic weights. Is there any confusion to you so far, whatever I have taught you now? Hello? Are you there?
So I have one doubt.
Yeah.
That if all the neurons are interconnected, then what actually differentiates them? Like, in a sense, all of them will be passing the same output.
No, no. If they are interconnected, say here, see this is getting weighted by this one, this particular weight. Input is of course same. Input is same, but weights are different. And finally, they're combined sum, so this will produce a different output. So this is what differentiate. Now, instead of speculating this in air, I'll give one particular problem, solve it. And we'll see it whether I'm giving a very simple problem to you, whatever I have done here, based on that only. So I have done solve a particular bit complex network. I'll give a very simple network to give an idea, to get an idea that whether this entire process we followed, does it really makes any sense, whether really system learns or not. So when I say system learns or not, how do you know that it is learning or not? Any rough guess? How do you know the system will learn or not?
By the error?
By?
By calculating the error?
Yes. Means in one, whatever the input you give and whatever the error you get, same error is being back propagated, and this after back propagation the synaptic weights will change. Now if I give the same input, now the error which I got in the first iteration, now the error should be lesser than that, isn't it? If that happens, then it comes, oh yes, it is learning. Now having said that, now take this particular problem and solve it now yourself. So let me take a very simple scenario. Let me call it as a x1, x2, this u, wa1, which assume that this is known to you, this is 0.1, and this is wb1, which is, let's say it is 0.4, and this value is wa2, assume that it is 0.8, and this is wb2, which is, let's say, 0.6, and there is only one neuron in the output. Let me call it a C. So this is your WCA. Let's say it is 0.3. I just randomly picked it. Don't worry about this. Initially, we have to put randomly, of course, under certain condition. So we'll see later all those conditions. CB equal to 0.9, and here is output. What is given to you is a one particular example which is having 0.35 and 0.9, and your corresponding D value is 0.5. You are required to find this updated synaptic weights for this. So apply the forward pass and apply the backward pass and tell me this updated values of all these four synaptic weights, and tell also whether your system is learning or not. Do it. I'm giving you 10 minutes to you to do it. Please do that.
So I was saying that if we initialize all the weights as same, isn't it possible that A and B will end up being same as well?
Do it. First of all, try to solve it. You are speculating unnecessarily. Whether it's
Okay.
happened or not happened, do it first. Okay? Because without doing simply your thought process, this is not thought experiment. This has to be done. So use paper and pencil and solve it first. Okay? Then you'll be able to get your answer. Hello? Hello? Hello?
Yes, sir.
Are you are you able to do it now?
We are still doing. I am still doing.
Oh, okay. Yes, Raghav, what is your status, bhai?
Sir, yet doing it.
Yeah, please. Anjali?
Sir, can you please minimize the screen once?
Yeah, please.
Yes, sir, on it, yeah.
Yeah.
So what should we take the neta?
Eta value initially, yes, I forgot to tell you. For the sake of convenience, you take 1 for the timing. You take eta value 1. Okay?
Okay, sir.
Okay, so I'll solve it now. It's already around more than 10 minutes. So now just compare your results with us and see. First of all, what you have to do is that if you remember that the whatever the generic example we solved, which you have assumed that it uses the activation function, which is sigmoid activation function. So you have to understand that or assume that phi of x or whatever each neuron is having activation function 1 plus e to minus x. For sake of simplicity, a equal to taken 1. Now let's talk about this a. So first of all, I have to, when we starting our this kind of calculation, we have to calculate the forward signal. So we need YA. So YA when I start, so let's say whatever will go first, we have to find VA. So, but instead of going V, I'll say within phi, I'm going to start this. So we'll say this 0.1 into the first component of this one, 0.35, 0.35 plus this weight 0.8 into the second component, that is 0.9. Okay, 0.9, which comes out to be within phi, it comes out to be how much it comes out to be 0.755 or 0.5. It comes out to be, and when you substitute for x here, you'll get the value 0.68. So likewise, you have to get the value of YB. So YB comes out to be 0.66, and you have to calculate the value of YC similar way, because for this YA YB is available. So accordingly, in terms of YA YB, YC will be done. So, or I should say YC is nothing but phi 0.68 into 0.3 plus 0.66 into 0.9, which comes out to be 0.69. So you have those values 0.68, 0.66, 0.69. Once you have this, so I hope you might have found this delta C. Delta C is nothing but DC minus the OC, right, into OC over 1 minus OC. OC is nothing but this is equal to OC itself, the output of the output neuron. DC is known to you, that is the C comparison value, that is 0.5, this desired value for this. So this comes out to be 0.5 minus 0.69, then 0.69, 1 minus 0.69, etc. All things you do, the values comes out to be up to 4 decimal places we have taken 0.0406. Okay, and of course now we are assuming that eta equal to 1. So we know that WCA plus, as per our this calculation, is WCA plus eta is, we have take let me write in general, is C, and I'm saying it is getting input from A. So YA, which I can write WCA plus eta is, I'm not writing, so delta CYA value WCA. WCA is 0.3, right? So we have 0.3 plus this value of delta C, that is minus 0.0406 into YA. YA is 0.68. So 0.68. This value comes out to be 0.2724. So see that CA, which was earlier 0.3, now it is reduced to 0.2724 due to this what you say error propagation. Likewise, I am writing direct value now, WCB, same process, and the value comes out to be 0.8732. So you got these two synaptic weights updated. So even this also value, which was 0.9, now it is reduced to 0.8732. Now what you're supposed to do is that you have to find a value of delta A and delta B. So you know that the process we have, delta A is nothing but YA1 minus YA summation K in the other one. So here there is a WKA. In the higher layer there is only one neuron, that is C itself. So I can write straight away here YA1 minus YA delta C WCA. Remember that whatever this C is going to talk talk about this updated weight which you have with you. So when you substitute all these things, value comes out to be minus 2.4 into 10 is to minus 3. It's very small value, so till this we represent. Similarly, we have to find the value of delta B because two neurons are there in this there. Okay, and once you have this, so delta V, which I already calculated, so this value, and you can verify later, minus 7.95 into 10 is to minus 3. Now, with this value, you have to find WA1 plus, which is WA1 plus, I'm not, and delta WA1, which comes out to be 0.1. You can say WA1, we have taken 0.1. So 0.1 plus eta is not there, delta A. Delta is this value, minus 2.4 into 10 is to minus 3 into x1. X1, what the input it is getting it. So x1, so I should have, instead of x1, I can write the value directly 0.35. So this overall value comes down to be 0.0992. In a similar way, I can have this A2 plus, and this value comes out to be 0.7978. Similarly, I have to calculate this plus B1, which is nothing but WB1 plus delta WB1 equal to WB1 plus eta B, and then y instead of y is x1. So when you substitute all this value comes out to be 3.3972. Similarly, plus B2 value comes out to be 0.5982. Now, so this synaptic weight, so these are the updated weights. So I'll write things so that it will be very clear to us. I'll write WA1. This value was, let me write this, 0. Let's see, 0.1, whereas WA1 plus means after error propagation, this value comes out to be 0.0992. WA2 was 0.8, and the updated weight is WA2 plus is your 0.7978, and likewise you do for the others, means that is listed. But what is the use? So this we have said that okay, synaptic weight is updating fine. So how do I know my system is learning? Now with this synaptic weights, let's say that you are changing the synaptic weights in this diagram, these values you are updating it. Of course, it will be updated automatically. And now just to check whether it is learning or not, let me apply the same input just to check whether it's learned or not, just to not back propagate, because it doesn't make any sense to back propagate once again for the same example. So we have learned this. So when I apply the same weight, so let me see that when I found the error initially that error was minus 0.19. How do I know this? Delta C, this value was the error, right? So this value comes out to be minus 0.19. And again, with this synaptic weight, updated synaptic weight, same input you applied, and you compare with the desired values and all. So value comes out to be, let's say E prime minus 0.1821. So you know that this value is more near to 0 as compared to this value. So you can say that error is reducing due to this synaptic weight updation. This is how the learning happens in the system, and over the period of time it captures the knowledge or the represented in the what should I say, in the training example on the data. So this is what we have done is very toy type example. Nobody is going to ask you to solve this for multiple thing in the system, maybe maximally 2 or 3 neuron system only that you have to do using paper and pencil. And that's why this needs a lot of computation power to do all this analysis backward, forward, and all these things. And there are many versions of this backpropagation has come where some of the synaptic weights which don't change, we obliterate them somehow. So this is how it's happening. So as I promised you that we have not only learned this the derivation during the last class, but now we have done with the paper and pencil that how a complicated neural network can be generally solved. And with this particular example, we have shown you that how this learning basically happens and how do we feel it. Now somebody asks, what will this happen and that will happen? Instead of that, me and giving the any answer off the shelf, I request you just do this analysis yourself and see what happens and infer accordingly. Any question here now? Hello? 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 Do you have any question? Okay. So before I proceed, I want to tell you something that from the next class onwards, as you know that we'll be asking the random quiz in between. So be there. And you know the same thing. This is not I have tried. It is we are asked to do that, so we'll do it. It's a good one way. And at random time I'll be asking. So the subject matter of those quiz will be the concept taught in the previous class. So remember always. So better is that before coming to the class, you brush up what we have done last class. So this you can assume that in next class when I talk about, so whatever we have done in the uh, BPA so far, so you can expect something on that. Okay, now let me go to the next part of it, and then we'll proceed to this part. So another 10 minutes we have, 10-20 minutes are there. So this BPA that we have seen that it's basically provides an approximation to the trajectory in a weight space computed by method of steepest descent, because the basic fundamental iterative approach which we applied to this is nothing but steepest descent. From that on, we say that a change in synaptic weight is directly proportional to the product of gradient and the input, right? From that only we came to derive this. But there is always a problem that for small value of eta, that is the learning rate, trajectory will be smooth, but learning will be slow. It will be smoothly, you'll be able to find it out. But because you're taking a very small baby step, it will take a lot of time to converse. Converse means, and convergence means when array is not changing anymore or the synaptic weights are not changing anymore. But on contrary, if you take the large value of eta, then large change in synaptic weight happens and such form that works maybe. The problem is that if large rate is happening, it becomes unstable also. Unstable means it can start overshoot the global minima and you get the start the error again rising up instead of reducing. So there is a simpler method of increasing the rate of learning, because why you want to increase the rate of learning is just to speed up the process of conversions. But at the same time, you don't want your system to become unstable. So there is a danger of instability is there. So for that, they have modified this conventional delta rule for backpropagation with by including a momentum term. Now, by including this momentum term, what you are doing that you are speeding up the process of learning, but at the same time, you are not compromising on the stability. How it happens that we'll see. So first of all, when it comes across, when I add to this, first we try to understand what does it mean? How do I understand that by including this kind of terms will help me in some way? So there are two approaches for me to analyze this particular equation. One approach is using jet transform. I just wanted to know, are you available of are you aware of jet transforms? Any one of you? Hello. Speak out here. I'm getting too annoyed. You don't speak. I'm asking a simple question. Do you know jet transform or not?
No, sir.
No, sir.
Okay, fine. So if you, because you don't know jet transform, so I'll apply a simple series analysis and see that which you are maybe familiar. Let's see that. So let's say this is the equation I have taken. So we'll start with the one particular value of n, and then we'll see this how this you can say that in a recursive way, this particular if I keep on expanding, what will happen? So let me take the value of n equal to 2 in a simple. for example, n equal to 2. When I take n equal to 2, you know that this particular equation becomes something like this: delta wj1 and this delta j2 y2. Now when this is there, so you imagine that only this part is this one, and further you can you can expand this in terms of this one. Okay, so when I do this, I'll be getting something like, so delta wj1, so alpha is this one, so I'll take this bracket entire thing, and as if instead of this one I'm replacing this entire part and changing value of n equal accordingly. So here this value has to be less than 1, less than whatever we become 0, this 1 1 plus, and eta delta j 2 2 2, let it be. Now again here this thing I can expand it. Now I can open this bracket, the alpha square etc. It goes into. Now again this delta wji has come. Once this has come, so what I can do it now, further I can expand it and see what happens. So you know that definitely this is 0 and this has to be less than 1, so it's 0 minus 1, basically minus 1. So I'll apply all this process once again till this minus 1, and let's see what happens. When I go for this, uh, does it make any sense to take the change in synaptic weight at minus 1? Does it make any sense? Hello? Hello? Because you are starting your training now at time 0. So before that, what is there? What was there? It doesn't make any difference because nothing was there. And you're starting from random itself initially. So we'll not consider this point. Even though if I multiply, it becomes alpha cube. This one, it doesn't make any sense to. So I'll consider only this point, and alpha square will get multiplied by this. So now I'm getting a equation in this particular fashion, right? So for this one, so let me see if I can generalize something from this. So this particular equation we can write, because the summation we can write it across, and you see here whatever the value of n is here is starting, the power of this alpha is also same thing, and as these things are going further, so it is keep on decreasing. So let me start at t0. So when I say t0, so alpha, and of course eta is common to all, so eta I can take it outside without any problem. So alpha power n minus t, or whatever the index you like, you can say this minus t minus here, because this alpha value should start decreasing. This alpha value should start decreasing, and this basically this is basically a momentum term. Alpha value start decreasing means what? So t0, so alpha n minus 0, so it remains same, whatever n is there same, plus when I go further it reduces by 1, when I go further it reduces by 2, like that. So this indicates this. Now the question comes, how does it matter, man? Like if I go for alpha and it's keep on decreasing, so as I told you, this alpha is a momentum term. Momentum term, so as you go for higher and higher, initially it will be fast and then slow, something like this. So you can imagine that way it is adding value. So we'll try to understand this. So but before this, so I'm trying to integrate this back to the equation, because we know this, that gradient of this error is this one. This we have already derived during your derivation of backpropagation, and we saw that delta G local gradient is nothing but something like this. If that is the case, we can write these terms either in this way or this way. It can be written in this particular fashion. If this fashion it can be written. So this is nothing but this particular part is nothing but here. Why we are writing this delta j yi, and in our formula here delta j yi. So instead of this, we can write in terms of this gradient only. So we are writing this generalized change in synaptic weight by this particular equation. Now we have to understand that what is going to happen here. Now this is a gradient, so we have to interpret it. So you write this equation somewhere on your page, so that when I talk about something in the next line, next page, it will be clear what is happening. Just write it, this equation. Please write this equation 15 on a page. Done?
No, sir.
This equation number 15, that's all. No need to write all these things. This you'll get through the handouts. So once you have written this, now I'll see. And remember this negative sign is there. So we have to interpret something beautiful about it. So from this equation, we can make this following observation. The weight vector is sum of exponentially weighted time series. Weight vector is sum of exponentially weighted time series. This is time series and exponentially weighted because L5 is there, so it is getting weighted every time it's getting added to it. And it's a time series because T is something depending on this. Now, for the time series to be convergent, the momentum constant must be restricted to 0 and 1. It cannot be beyond this momentum term because you know that the series analysis probably in mathematics in first semester you might have done this Maclaurin series or some Taylor series, etc. Convergence condition you might have seen. If it is the time weighted and it's a function of series, is a series, so you have to put some condition that under what condition it could be convergent, otherwise it will keep on going, right? So also this gradient dou E by dou WJ has the same sign whenever it has same sign in consecutive iteration. The weight update is accelerated, speed up downhill. So what do you mean by this equation again? If in a two consecutive iteration this gradient remains same and you know that this is negative, so you are making change in the synaptic weight with a large value in the negative direction, means it is accelerated. Okay, but if this value is once negative, once positive, so this becomes negative and positive, so the value of synaptic change will happen in a small by small amounts. That's why I mentioned here, when this value has opposite sign on consecutive iteration, the sum shrinks in magnitude because it's a minus plus in those things. So weight is adjusted by small amount. Now the inclusion of momentum in BPA has a stabilizing effect in the direction that oscillating in sign. So it basically is also take care of that kind of oscillation. So this was the all about this when we add the momentum term, how things changes. I hope you understand this. Now the sequential and batch mode we have already discussed about this, so I'll not talk about it. So remember this, whatever the example I have explained, or first of all derived this BPA, we have used this sequential mode of training or what we call it online mode of training. For the batch mode of training, things are slightly different. You know that entire training is done, all those values you write, and at the end of the day, you saw this one update the synaptic width in one go. So, but what that is epoch by epoch happens, but in case of sequential, it is example by example. And there are some, it's basically it's a repetition what we have already done it, but it's good to repeat it, this top part. So in sequential mode, update rule applied after each input output presentation means each input output example. Order of presentation should be randomized. And benefit it has, of course, there's no storage issue. And of course, the stochastic search through weight space helps avoid local minima, which chances are there that you'll be able to go for local minima stock up in case of batch mode, but that doesn't happen here because randomized and you're changing every now and then. And disadvantage is that it's basically hard to establish theoretical convergence condition when you go sequential mode. But also we have already discussed that it is a preferred mode when the training data are redundant. That is, data sets contain several copies of exactly the same pattern. Why it is useful for that? Because same copy and multiple things are there, so you don't subject for training all those similar copies. You subject only one, but this you can't do in case of batch mode. Batch mode, entire batch has to go. You don't worry about this whether redundant is there or not. But here and batch mode, you know, update rule applied after all the input output presentation, and some benefits are there that this gives accurate estimate of gradient and convergence to local minima is guaranteed under simple condition here. And you know that this particular example we use, and this is basically synaptic weights for when you go for this synaptic weight defined by this particular delta rule when you go for this kind of stuff. Stopping criteria, when we say is this, we cannot be shown to converge, and therefore there's no well-defined stopping criteria as such. But okay, more on this I'll discuss tomorrow in the next class. We'll see. We'll stop here itself because again I'll have to go for many other things to talk about. So we'll see.